Okay, so in this video, we are going to talk about the capacitive elements that can be used for designing passive transducers. Up till now, we have studied what are active transducers, what are passive transducers, and how the resistive element can be used for designing passive transducers. Right, so the second passive element of electronic circuits is a capacitor, and the capacitor can also be used for designing a variety of passive transducers, right? So over here also the basic fundamental remains the same. That is, we have to design a transducer in such a way that the physical quantity that we want to measure, whether it is temperature, pressure, okay, humidity, or maybe flow level, or whatever physical quantity we want to measure, that should in some way or the other affect the capacitance of our capacitor that is connected into the circuit, and that change in capacitance will actually give rise to change in the voltage, right? And that we can measure and then map with the input quantity. So a capacitive transducer, we all know it contains two parallel metal plates. You all know what is a capacitor. You must have studied in your preliminary classes. So the capacitive transducer, it contains two parallel metal plates. These plates are separated by a dielectric medium, which can be either air, gas, liquid, or any solid material. This transducer, it uses the electrical quantity of capacitance for converting mechanical movement into electrical signal. Other than mechanical movement, also you can measure certain quantities, right? So the idea is that the physical quantity will actually affect the capacitance in some way or the other, and that will result into a change in the electrical signal, right? So the capacitive transducer, it works on the principle of variable capacitances. That is, the capacitance, it varies with respect to the input signal. The input quantity causes a change in the capacitance, which is directly measured by the capacitive transducer, and the capacitance of the transducer changes because of many reasons, like overlapping of plates, change in the distance between the plates, and the dielectric constant, right? So these parameters we can understand better if we just look at the basics. The principle of operation of capacitive transducer is based on the familiar equation of the parallel plate capacitor. You all must have studied in your earlier classes what a capacitor is, right? You can see in the figure, you have a parallel plate capacitor over here. You have two metal plates, and in between there is some dielectric medium, right? And when you pass the current through it, there is a quantity called capacitance that is developed in this particular device, and the capacitance is governed by the equation that is given over here. Okay, epsilon naught epsilon r into a by d, where d is the distance between the plates, capital A is the overlapping area, epsilon naught is the absolute permittivity, and epsilon r is the dielectric constant. This depends upon what material you are using as a dielectric in between the two plates. Right. So this is the basic governing formula for any capacitive transducer. Now from this formula, you can see epsilon naught, epsilon is a fixed quantity. Epsilon r is a fixed value depending upon what material we are using, and A and D are the two things which the capacitance depends upon. So from this formula, we can find out that basically a change in capacitance in any capacitor can be induced by in three methods. Firstly, you can change the overlapping area of the capacitor plates. Second, you can change the distance between the two plates. And third is you can change the dielectric constant, that is epsilon r. So dielectric constant will change if the medium or the dielectric material between the two plates changes. So these three fundamentals we will be using for measuring our physical parameters, right? So whenever you're designing a capacitive transducer, you have to think over that your physical quantity that you want to measure, for example, it might be a mechanical movement, it might be some pressure, okay, that should be connected to the capacitor in one of these three ways. Either your physical quantity should change the overlapping area, or it should change the distance between the two plates, or it should change the dielectric material in between. That will automatically change the dielectric constant. So any of these three changes, if they are occurring in a capacitor, corresponding to the input that is coming from your physical quantity, it will result into a change in capacitance, and that change in capacitance will be reflected in terms of the effective voltage of that particular circuit. Okay, so we'll just go through one by one all these three formulas. So how do you change the overlapping area? You can see in the figure we have two parallel plates and there is air in between. Air of course acts as a very excellent dielectric material. So what happens is if one of the plates I connect to my device for which I have to measure the displacement. Right. Now, in this case, you can see if the top plate is connected to the displacing element and the movement is taking place in horizontal manner. So, as my displacing element will move in the horizontal plane to and fro, the top plate will also move along with it. When it moves, for example, over here, you can see that the top plate has moved half out of the overlapping thing. So, the overlapping area of the two plates actually reduces, right? It is all in this figure. You can see almost half of the overlapping area is only left, right? So if the area is changed, the overlapping area is changed, it will lead to a change in the capacitance. Okay, so the capacitive transducers are used for measuring large displacements, approximately from 1 millimeter to several centimeters. The area of the capacitive transducer changes linearly with capacitance and the displacement. Okay, so the displacement will actually change the overlapping area, and that overlapping area will actually change the capacitance. Now this relationship between area and the capacitance is linear because if we are considering the fact that the dielectric is constant in between, so epsilon r and epsilon naught will actually become constant values, right? And so you can say that the capacitance is actually linearly varying as along with the overlapping distance, right? So there is a linear relationship between the two. So the transducer, it changes linearly with the capacitance and the displacement, right? So the you can see the equation that is given over here. This equation actually shows the capacitance is directly proportional to the area of the plates. It changes correspondingly with the change in position. Okay, so this is one of the methods by which displacement we can measure. Displacement changes the overlapping area changes the capacitance, and capacitance ultimately reflects into a voltage change, right? So second method could be a transducer using a change in the distance of plates. That is, now in earlier what we were doing is that we were changing the position of the plates with respect to each other, okay, in terms of the overlapping area. Now what we do is we keep the overlapping area constant, and the moving the element of my field is actually connected to one of the plates, and that displacement is taking place in terms of the distance between the two plates. Now in the figure that you see, the blue colored plates, they are actually the capacitor plates. If I fix one of them and the second one is connected to my displacing element, as the displacing element moves, this moving plate will actually move to and fro. So the distance between the two plates will actually change, right? And since it is inversely related to the capacitance, you can see that as the distance decreases, the capacitance will increase. As the distance decreases between the as the distance increases, the capacitance will decrease. So the more the moving plate goes far away from the fixed plate, the capacitance will decrease. Okay, and the more it comes closer to the fixed plate, the capacitance will increase. So you can see that as the distance between the two is changing, the corresponding change in the capacitance will result in a fluctuation in the voltage of your circuit, right? And the third one could be change in a dielectric constant. Now, dielectric constant, how it is going to change? Dielectric constant is actually a constant value for any one specific material. So, if the dielectric material between the two plates is changing due to some means, the constant will change in the formula, right? So, over here you can see that the dielectric material in between, suppose this is a slab of some solid material, this particular dielectric slab is actually connected to my displacing element. So when my displacing element moves, actually this dielectric also moves. right? And so you can see that in this figure, as the dielectric is moved out, there is a change in the dielectric constant. Now you can see it is now acting as two capacitors connected into parallel. One is having some dielectric, the other one along with that is having dielectric, is air. Okay, so this capacitance will be different as compared to if the complete dielectric slab is inserted between the two. So my displacing element when connected to the dielectric slab is actually creating a change in the dielectric constant of my capacitor, and that will represent a change in the voltage. Okay, this is the governing formula for the change in capacitance with respect to the change in the displacement of your dielectric constant. So this kind of method, one very popular example I can tell you, that we can use this particular method for level measurement. For example, if you have a tank, right, on both the edges and you want to measure the height of liquid, suppose. So what we can do is we can, on the both the edges of the tank, I can place two metal plates which are going to act as a capacitor. Now when up to that particular height, where up to where we want the liquid to rise, till that height up, when there is no liquid, the dielectric is air, so capacitance will be something else. As your tank goes filling up and the level of the liquid reaches that particular point, that means the area between these two plates now gets filled with the liquid, the dielectric between the two plates changes, the dielectric constant changes, and the capacitance changes, right? So that is a one very popular application of the capacitive transducer in terms of level measurement, right? So likewise, you can, if we summarize from this picture, it will be more clear. If you have two parallel plate, capacitor, you have a capacitor with two parallel metal plates. One possibility is you can have vertical movement. That is the first one. The capacitance will change with the distance between the two. Second, you can have horizontal movement where the capacitance changes due to the change in overlap area. And third is where the dielectric slab in between is actually moving and the plates are fixed. So the capacitance will change due to the change in dielectric constant. So these are the three basic methods with the help of which we can measure, the physical quantity with the help of a capacitive element. So we have a lot of advantages as well as disadvantages for using a capacitive element. Let us look at the advantages first. It requires external force for operation and very useful for small systems. Capacitive transducer is very sensitive. It gives very good frequency response, because of which, it's very good for dynamic study. Dynamic study actually means where your input is changing very fast. If there is a dynamical change in your input, capacitive element actually gives a very good output in those cases, right? Then the transducer has high input impedance, and so there's a very small loading effect, and it requires a very small output power for operation. Whereas we have certain disadvantages. The metal, since we are using metallic plates, so a proper insulation is a must. Otherwise, it will start disrupting with other elements of the circuit. The frame of the capacitor, it requires earthing for reducing the effect of stray magnetic fields. That means any extra current, any extra magnetic field, if it is being produced, it should be directed towards the ground. Sometimes the transducer shows non-linear behavior because of the edge effect, which is controlled by using the guard ring. Now, edge effect basically means that at the it might not be a very smooth transition or a very smooth exact value. Okay, because at the edge there is a transition taking place, so there might be certain non-linearities coming up into your calculations because of that. Although most of the times it's very small in magnitude. The cable connecting across the transducers can also cause an error, because sometimes the cables that you're using, they within themselves they become a capacitance, and they start introducing some disturbing capacitance in between. So that needs proper insulation. That is one of the disadvantages. So in total, we can say that a capacitive transducer can be used for measuring both linear and angular displacements. We have seen that it is very sensitive, and it can used to measure even very small magnitude of distances. Then force and pressure, it can also measure. The force or the pressure is first converted into displacement, and then displacement actually changes the capacitance, right? Pressure transducer, it can be used as a pressure transducer in some cases where the dielectric constant of the transducer actually changes with pressure. There might be a possibility that you have maybe some substance in between acting as a dielectric, which is, very sensitive to pressure. So when you apply pressure to that particular element, the dielectric constant, because of certain internal atomic changes, the dielectric constant changes for that element. Okay, so directly that kind of a the element can be used as a pressure sensor. When pressure is applied to that sensor, the dielectric constant changes and correspondingly the capacitance changes. So that was all about the capacitive passive transducers. That is how we can use a capacitor for designing a passive transducer for measuring various physical phenomena.